Okay, so let's get started. So you have all seen this graph before where I showed you the RMS data for a wall bounded turbulent flows, and we have discussed that there is something called anisotropy where the even in a flow like a turbulent plane coed flow or any other turbulent boundary layer, you will get this URMS, VRMS, WRMS or of different not orders of magnitude, but the values are like twice or thrice of that one, but they are of the same order of magnitude that we discussed. And y is the wall normal direction. So now, in addition to this anisotropy that we discussed, okay, there is something else that you need to look at in this graph. So as this is the wall, okay, at y equal to 0, this is the wall. So as you approach the wall, what do you notice here in the data here? U is the, if I write the coordinates x direction, y direction and z. So in the x direction you have the URMS, this is the VRMS, and the WRMS is the out of plane component. So what do you notice as you approach wall, as y approaches 0 in the 3 graph? Only as you are coming close to 0, see what do you notice here? Anything very peculiar thing that you observe? Look at the way the data is damping, right? You are approaching the wall, y is tending to 0 and the graph starts to damp, that means the URMS starts to damp. Similarly, the WRMS, that is out of plane, VRMS is also damping. Are they all damping at the same rate? No. Is it something like one which is damping much ahead of the other two, right? Which is that one? URMS? No. VRMS. See, the VRMS starts to damp much ahead. So this is where the data is not exhibiting any damping, right? Let's say from the y by h 0.5 and above up to the channel center line. So here you see it is more or less constant, the VRMS, WRMS and the URMS. But as you come closer, the VRMS is already started to damp far away from the wall, okay? But the URMS rises and drops very close to the wall, right? So the damping is occurring only from here. Similarly for a WRMS also, let's say somewhere here, right? But the VRMS starts to damp much ahead, right? So the damping is occurring. Damping of VRMS is occurring much ahead of URMS and the WRMS, or in other words, the wall normal fluctuations are damping faster than the wall parallel ones, right? So the wall normal fluctuation, that is your V prime, or damping faster than wall parallel ones. It is your U prime and W prime. So why does this occur? Does this occur in every flow where you have a wall? That is, we have to see, and this feature must be taken into consideration by your model, because this is the physics that I am discussing, okay? So this particular feature, is this any doubts on this before I move to the next slide? This is what we see it in the data, that the VRMS, that is a wall normal RMS quantity, is damping faster, coming to 0 faster, because you see it is, look at the slope, it is coming to 0 faster compared to the wall parallel ones, okay. So this particular state of turbulence is called a 2-component limit. two component limit. This was discovered by John Lumley. There is also a turbulence theory book written by him. So this two component limit, what does this say? That means two components are behaving in one fashion in a wall bounded flow rather than the other component. That is, the wall parallel components are damping in one fashion, and wall normal turbulent quantity is damping at a different behavior, right? So this state of turbulence is called two component limit. So what this means is, as we approach wall, the wall normal stress goes to 0, that is V prime square goes to 0 faster than the wall parallel ones, that is your U prime square bar and W prime square bar. So this state of turbulence is called two component limit. Wall normal stress goes to 0 faster than the wall parallel. All right. So this particular thing happens in two different ways, and before that we will see that how general this is, because if you want to model this, you need to make sure that this is occurring for all types of flows where a boundary layer is present, a wall is present, and this is true. Exception for this can be where you have stratification or Coriolis force. Okay, so this occurs, note here. Okay. Occurs in all turbulent boundary layers except when Coriolis force or stratification is present. So this is common, right? Not everybody uses Coriolis force in their calculations, except let's say you are doing turbo machinery or atmospheric flow, right? Special cases, or not everybody is looking into a flow where there is stratification. So in general, this is common, you can say, right? So in general, this occurs. This phenomena, two component limit, is more generic compared to whenever you have a Coriolis force or a stratification effect, right? So that means this has to be considered for modeling. And does your model models this? So eddy viscosity model has a problem because the isotropy is enforced through eddy viscosity and turbulence kinetic energy in the Boussinesq, right? So EVM models have, you can say, eddy viscosity models has an issue here. Since isotropic behavior is you can say encouraged by your eddy viscosity nu t and the turbulence kinetic energy K in the Boussinesq. right? So you have minus 2/3 K in the Boussinesq. You have also have eddy viscosity, which is lumping turbulence as a scalar quantity, and we clearly see that VRMS has to damp. So turbulence kinetic energy, when you are computing, it is a sum of all the three stresses. Where some isotropic behavior is enforced means that it may give higher turbulence than what is necessarily there, because V is now much smaller, it is damping much faster also. So the actual turbulence kinetic energy can be much lower than what your turbulence model, eddy viscosity model, is predicting. Therefore, it requires something to be done. Okay. So this particular two component limit occurs due to two different reasons, right? So two component limit, or you can say two component state of turbulence, occurs due to two factors. One, so there are two types of damping that is occurring here. One is that there is of course viscous damping for all the three components. So there is something special that is occurring for the wall normal component, that is the, so this wall normal fluctuation or the VRMS, so this feels the wall far away from the wall. So the wall parallel ones, that is your URMS and the WRMS, they feel the wall as it approaches the wall very close due to viscous effects. So there is viscous damping for the wall parallel stresses or wall parallel turbulent components, but the wall normal one feels the wall far away from it because of the pressure field. So there is a pressure damping that is occurring for the wall normal fluctuation, but the wall parallel fluctuation gets only viscous damping, and viscous damping is present for all the three components. So it is the pressure damping that is the major reason for wall normal stress to go to 0 faster. That is why the curve starts to damp much ahead. So that is far away from the wall, the curve is already started to damp for the VRMS, but the URMS and WRMS very close to the wall it is dropping, right. So first thing is damping of V prime square bar occurs far from the wall that is, you can say about y plus about less than approximately equal to 200. So it is much away from the wall through the pressure field or pressure damping. And the second one is of course the viscous damping that is present. Viscous damping occurs close to the wall, that is about y plus less than equal to approximately 20, that is, let us say the middle of the buffer layer to the linear sublayer when it is dominant viscous effects, and that is dominant for all the three RMS quantities. So this first one is the critical for the V prime square average component. Okay. So this has to be considered by your model, right. So all models must capture this behavior, capture or predict or even accommodate, may not be able to predict, or you can say account for this behavior. Capturing is possible only when we are actually calculating all the three stresses. So in eddy viscosity models we are computing only turbulence kinetic energy, so it must account for this behavior. If you are solving Reynolds stress equations, then it must also predict or capture that behavior. So how is this achieved in the RANS models? Is there are three ways of doing this. The first is in the eddy viscosity models. in the eddy viscosity model. In this one, we need to do what is called a low Reynolds number formulation. Okay, so low Reynolds number, you can say L or N models. So what this low Reynolds number models this is that they introduce a damping function here. A damping function is used to account for this phenomena. In low Reynolds number models. Okay, so here low Reynolds number does not mean, as we have seen in the wall function description, low Reynolds number only means locally low Reynolds numbers. Low RE refers to locally low Reynolds numbers, that is in your near wall zone, right? We are not talking about the global Reynolds numbers, your RE delta and so on. And this damping function is now used for all types of eddy viscosity models, that is your typical K epsilon, K omega, all this type of models. So another option that we have is to go into, this is also an eddy viscosity model, so I can say this is A, where you are having, this is for the two equation models. Okay, two equation eddy viscosity models, that is your K epsilon, K omega, etc. Any other type of two equation models. The other option in an eddy viscosity model is actually to solve one more transport equation for the VRMS. So this is called a V2F model. This is actually a 4 equation turbulence model. So it's a 4 equation, that is 4 transport equations are there, that is K epsilon, V prime square average and F, 4 transport equations, or K omega V2F and so on. So 4 equation transport model. So you are actually computing for V2F, and then V2F is used to participate in computing the eddy viscosity. Okay, 4 equation means, like for example, K epsilon V2F or K omega V2F and so on. So here what we do is V prime square is used to compute eddy viscosity. So that eddy viscosity is taking into account the this enhanced damping factor, and eddy viscosity occurs in everywhere, Bussiness assumption. So it occurs in production rate of turbulence kinetic energy calculation, wherever eddy viscosity is coming, is naturally accounted for. So that is the philosophy behind this model, a 4 equation transport model. And the other option within the frame of RANS models is to use what is called a Reynolds stress model. Okay, Reynolds stress model. So as the name itself says, you are solving for the Reynolds stresses. So this will be a 7 equation model. There are 6 Reynolds stresses that you have to solve. In addition to that, we will solve for an epsilon equation. We will come to that when we move to RSM. So in a Reynolds stress model, you are of course computing for all the stresses. There is a transport equation for each stress, and that means when you are calculating that, there is a pressure strain rate term. So you see in turbulence kinetic energy equation, the pressure strain rate term was gone, right? The redistribution was not there. So when you are computing Reynolds stresses, that term is present, which will handle this. Right? For this one, so damping is ensured. Damping of V prime square bar is ensured by the redistribution term or the pressure strain rate term. So this will naturally do this in a Reynolds stress model. You are computing for all the stresses and there is a pressure strain rate term. So before going into this, first we will see we already have a K epsilon, K omega type of model. So we have already seen in an industrial flow we don't want to capture near wall effects, and near wall effects are displaced away from the wall using wall function, and that we call high Reynolds number models, HRN, or high Reynolds number formulations. As against that, when you are capturing the near wall effects, we call it low Reynolds number models. The same, there is an LRN K epsilon model or a high HRN K epsilon model. Here, of course, you should not use wall function. You need to capture the near wall behavior. So we will go to what is called a low Reynolds number model. Is this clear so far? The physics and the approach how we have to do this? Okay.